I want to talk about this paper that was just released in Nature Online, Nature magazine. And for those of you who don't know, Nature is one of the two main top publishers of scientific research. So if you're a research scientist, your ultimate goal, if you're in the life sciences, is to get your paper published in Nature. If you're in other sciences, you want to get your paper published in Science. So this was in Nature. These guys made it. And the title is Power Generation from Ambient Humidity Using Protein Nanowires. Now, in a nutshell, what these guys discovered is that you can get seemingly free energy from a device that they constructed. Normally that would seem like science fiction, and we would throw this in the garbage, but it was published in Nature, okay? And in fact, they had to work for a while. It was received in 19th of November of 2018, and almost a year later, November 14th of 2019, it was accepted by Nature. So, and the way this usually works, for those of you who don't know, if Nature's interested in your article, they'll come back and say, okay, we want this, this, and this clarified. You need to do this experiment, this experiment. So these guys had to take a year to do all these extra experiments and things that were outlined in Nature. And I'm pretty sure those are the source of these extra 27 pages of supplemental material. Most of this the whole paper is only like 4 pages long, but the rest of it is all supplemental material. And I'm sure all those figures were extra experiments and things that were demanded by Nature before it was deemed official. And for something of this magnitude, yes, that makes sense, okay? You want to have this proven backwards and forwards, up and down, through and through, and know how it works before you just throw it out there. And so here it is. What is it and how does it work? Basically, these guys, the reason it's in Nature is because these are life scientists. I'm one of the main researchers, Dr. Lovley from University of Massachusetts. Yeah, Derek Lovley. I watched an hour-long talk of his online about this that was posted a few years ago on YouTube. He studies bacteria, microbiologist, and he's interested in microbiologists that break down things like plastics and minerals and stuff like that. So he studies like Geobacter pylori and bacteria and stuff that basically these bacteria that he's interested in produce nanowires, which means they have these little hairs that are like nanometers in diameter that stick out from the bacterium and interact with the environment and conduct electricity. And in the case of these bacteria, you get a bunch of bacteria in a soup, and they produce basically this network, this mesh of nanowires. And the researchers, basically, they discovered properties of the nanowires themselves. So they don't really care about the bacteria at this point for this technology. For this technology, all they do is purify the nanowires. So I assume that means they throw the centrifuge or something and get it to the point where the bacteria and debris pellet out, and all that's left in solution is the nanowires. So then you can like pipette off the solution, and you've got a solution that contains all these nanowires. And then what they say in their experiment is they inject the solution onto some kind of a substrate. In this case, it's a plate of gold because they need a conductor inside of a channel on a glass film. For people that deal in thin films and stuff, this is going to be old hat. This is probably all very standard procedure. So basically, you have your solution of nanowires, you pipette out a certain amount onto your channel and let it dry. And so basically, then what you end up with is this dry film that contains nothing but the nanowires that are a certain thickness. And the thickness depends on how much you inject it. And they tried all kinds of different thicknesses and stuff and settled out at a thickness that's around 10 micrometers in thickness of this mesh of nanowires. And each nanowire is something between, I think, 1 and 3 nanometers in diameter and, I don't know, 10 to 40 nanometers in length, something like that. But it doesn't matter. They all form this mesh, this like network that has electrical properties. And the property that they accidentally discovered in the lab a few years ago was that this stuff, under the right conditions, just generates electricity on its own. And they saw it doing it, and they tried to figure out, so what were the conditions? So basically the conditions they found were, if you've got a conductor on the bottom, like a plate of gold, and then you've got your thin film of these nanowires on top of it, and then you've got another gold conductor on top that doesn't cover the whole top. That was a critical thing. So you just have it cover like part of the top, like a strip of gold across the top for your conductor, and connect electrodes to the gold and the on the top and bottom. Your whatever you want. The ends of your multimeter. Put one tab on the, one pin on the top, the red on the top, the black on the bottom, whatever. You will get a current coming out of this, just sitting there in normal air. And they found out that sometimes it produces more and less current. And well, what was the conditions? And they figured out after a while that it was the ambient humidity that determined how much it put out. So basically, if you've got no humidity, perfectly dry air, it doesn't conduct anything. If you've got somewhere around 50% humidity, it conducts quite well. And you get a current that's maximal, the maximal current you can get out of it. And then if you've got up to 100% humidity, you're down to like 10 or 20% of your maximum output, something like that. But it still works. So that was where they were at when I saw the video on YouTube. That was kind of about these bacteria, and they just mentioned that in passing at the very end of the presentation, because they didn't know how it worked, the fact that they could get electricity generated out of it. So at that point, they really worked on figuring out how it worked, and that's what this paper is really about. Other than just kind of describing overall what the apparatus is, they really go in depth into how this current is getting generated. Obviously it's not magic. It's not free energy. It's got to come from somewhere. So where's it coming from? And they actually found related research. There are guys that have been researching extracting electricity, harvesting electricity from humidity gradients before. And there are different technologies where you basically for instance, get your strip of paper stuck in water on one end and dry air in the other, and you can get a current going through it. But, that type of thing. That's a very crude example. And the best the guys could do in the past was to get basically a spike of electrical output that would last about 50 seconds long, less than a minute. And then it would be gone. And then it would take like, a couple minutes to recharge, and longer to recharge, and you got electricity out of it. And so you're sitting there going back and forth, like, getting this wet, getting some current, letting it dry out, getting it wet, getting some. It wasn't practical for any kind of real generation of energy. So that would be useful, economical, productive. Now, what they discovered was unique about this material, these nanowires, this nanowire mesh, is that it is very selective about how it allows water vapor into the interior of the material. So basically what they discovered is, with this nanowire mesh that they have, if you've got the mesh sealed on the bottom underneath, so it's up against like a gold plate, glass, whatever, so it's isolated from the ambient humidity. And then you've got humidity up above it, like 50% or so, optimally. What happens in this nanowire mesh is you get this gradient of moisture. So it's the same moisture content approximately as the ambient humidity. Actually, it's actually less than that. It's like 27% when it's saturated at the top of, basically that's the mass of water vapor in the mesh relative to the mass of the mesh. It's about 27% at the top, and then that will get less and less. It decreases and decreases and decreases because of the nature of the porosity of this mesh. The water vapor just can't get in. It has a harder and harder time getting in through this mesh until you get down to, just off the top of my head, something like 15 micrometers, which is not very deep. You get about 15 micrometers in, and then you're down to like 3% of the weight of the water vapor in that material versus the weight, the mass of the mesh. They call that, oh, they have a figure for it. I can't remember. I'm not going to get into the technical part. But so at that point, if your film is thicker than that 15 micrometers, it doesn't really help you very much because you'll just end up with your gradient at 27%, 15 micrometers deep, you're down to 3% concentration of water vapor, and then it's 3% no matter how much thicker your material is. So as far as usefully getting more and more electrical current, which you want a steeper gradient, your steepest gradient is about 15 micrometers deep. So a film of about 15 micrometers of this nanowire mesh that's all you need. That's the maximum amount you're going to get benefit from. So your device that generates electricity ends up looking like this. They've got pictures somewhere. Maybe I'll find one, but I can just describe it right off to begin with. To begin with, you've basically got your a substrate, which could be I don't know, glass, silicon, whatever. So something really thin. They use a substrate that's less than 2 micrometers thickness. In their experiment, so you could have like a 1 to 2 micrometer thick substrate of silicon or something. They use plastics, glass, whatever. And then on top of that, you've got a thin layer of your conductor, which they use gold because it's inert and whatever, but you could use aluminum, whatever. They even use carbon just to demonstrate that it didn't have to do with the gold. And carbon printed on a printer, a special printer setup. You print a layer of carbon on the gold and then print it on a piece of paper on top, and they still got it to work. But anyway, so you have your conductor, you have your substrate, a micrometer or so thick. You have your conductor, which the thickness, I'm not sure exactly what that was. I assume it's around the same 1 micrometer thickness or something. It's just a film. And then on top of that conductor, you've got your thin film of your nanowires, which is going to be, in their experiments, they used like 5 micrometers thick, between 5 and 15 micrometers thick of that. And then you need a certain amount of air above it so that it can pull ambient humidity in that will adsorb, not absorb with a B, adsorb with a D, which means it just kind of collects on top of the thin film, nanowire thin film, for it to pull in, to continue to pull in the ambient humidity. For that adsorption, you need, what they found is a thickness on top that's about the same as the thickness of your thin film. So you would need a good 15 micrometers of air gap above. And then you could, if you want to stack these cells on top of each other, you could start it all over again. So in my diagram, basically, I was kind of using a ballpark figure of their practical results. I got right here something that's about 35 micrometers for each cell, and then you can just repeat and stack those 35 micrometer cells on top of each other. And I use that for my math to determine how much power you can get out of a three-dimensional object. And what size does your three-dimensional power brick have to be to get a certain amount of power? And I did a bunch of calculations with that. Sorry I didn't make time to prepare cool slides or anything. I just wrote this out on a sheet of paper. So what you've got, I've got all the math down here for how I calculated based upon they have two values they basically give. They give their experimental value for the amount of electrical current, basically the wattage they could get per square centimeter and they got 5 microwatts per square centimeter experimentally. They did the math. They figured out how all this works, like molecularly and everything, and the physics. And so then they could model the system, and figure out, optimally what's the maximum amount of energy here that you can pull out of this system electrically. And so if you are 100% efficient with your design of this system, using the materials they have with the nanowire mesh they're currently using, and everything, you could get up to 120 microwatts per square centimeter. Okay, so then you can calculate, if you know that, you can calculate how much power you can get per cubic centimeter. Using this 35 micrometer thickness gives us approximately 286 of these cells that you could get stacked on top of each other in 1 cubic centimeter. Okay, and so then you can multiply your 5 microwatts by 286, and you get 1,429 microwatts per cubic centimeter with their current setup that they got experimentally. Theoretically, they calculate you could get 34,286 microwatts per cubic centimeter. Okay, and so using those two figures, I made a table here using some common devices and their electrical consumption. So, and I converted it all down to something I understand better, which is like cubic inches and cubic feet, which makes sense to me, but you can do the math and do the conversions yourself and do your own sizes. But so for a smartphone here, a smartphone consumes around 6 watts. I assume that's when you're using it, like playing a game or something. I could be wrong. It could be more of that. That could be an average. Whatever. It's on the order of 6 watts, which would translate with their current design that they can use, that they've got experimentally. You would have a power brick that's approximately 253 cubic inches. Okay, yeah, I'll stop holding this up. You can just go back and refer to it if you want. And 253 cubic inches is like, imagine a solid cube that's about 6 inches on each side. That would be a brick about that size to power a smartphone. Bigger than you would want to stick in your pocket, obviously. I believe that's right. I did the math over again, came up with like a little over, about 0.6 of a cubic foot, of a foot on each side, whatever. And then theoretically, you could get this down to 10 cubic inches, which is a lot smaller. That's closer to, imagine a little power brick that's 3 inches by 3 inches by 1 inch. That'd be about 9. So it'd be something like that. And that's more of the, you're getting close to the size of a phone. It'd be like a fat phone. It wouldn't be optimal. But keep in mind, one thing I wrote in my note here, and I don't know if you can read it or not. I just want to get this up here for people that like reading things. So what that says is, note these are for continuous power output. You could use capacitors or batteries to even things out and make your power brick made with the thin film, nanowire thin film power brick could be a lot smaller, because then you can just keep a capacitor powered up, and then when you have some peak use, like you get a phone call or something, or you're playing your game for a while, you can drain your higher power capacitor, or even like a more conventional battery in the phone. And then when you're not using it, it's sitting in your pocket or whatever, it can be recharging with this other method. If you use that result, then you have something like 1/10 of the size. You can get down to sizes that are practical to attach to a device, and that's what I found overall. Let's go on. Another device I found is a house. Your average house consumes about 1,500 watts. That's just a ballpark figure. Somebody like me, I waste a lot of electricity. It might be closer to 2,000 watts. And that means that's how much I'm sucking out of the line all the time. And when they figure out kilowatt hours, they figure out, if you're taking 1,000 watts per hour, that's a kilowatt hour. You do that over a day, you consume 24 kilowatt hours per day. That's where that measurement comes from. So you can just get down to watts, because this stuff produces power continuously, these power bricks. So really all you need to know is the watts, because so basically if you have your home that's consuming about 1,500 watts all the time, then you would need a power brick that was, with a current method, that was about 37 cubic feet, and that is about the size of a stove, an oven, or maybe a little smaller than a refrigerator, or an old-fashioned furnace. So you can imagine something like that size sitting in your basement or whatever, or if you're building a new house, you could just build that into the floor. You wouldn't even notice it. The floors could just contain these power packs or whatever. And then you wouldn't need a furnace. But that way I would even, don't get me started. This gets us to some incredible things here. But so just imagine you're consuming just your electrical needs. Let's say you've got conventional furnace and everything right now. Just your normal electrical needs are about 1,500 watts. You have a power brick about the size of a refrigerator. If you had that sitting in your basement, you could unplug yourself from the power grid. That would be all your energy needs. So you can be out in the middle of nowhere, Siberia, Northwest Territories, Antarctica, the middle of the desert, the bottom of the ocean, anywhere, and you can have this refrigerator-sized power brick sitting there. It's going to give you all the electricity you need for a conventional home. And then you tell me, oh, but hey, if I'm in Siberia, it's going to be cold, and I'm not going to be able to get natural gas, out to me. Where do I get my heat? Well, I say to you, aha, yes, there is such a thing as electric heat. In fact, a lot of homes use electric heat, and your power consumption will go up quite a bit. I didn't put that down. I figured that out yesterday, the power consumption of electric heater and stuff, and it came down to for a room, you would need 1,500 watts to heat a small room or something like that. So that's why I was talking about the architecture of a house, because your 1 cubic meter, about the size of a refrigerator, that can be spread out to the size of the floor in a room, okay? And then you've got tiles that are only a few inches thick, and you could just incorporate those into your architecture, and those could just have a heating element on top, and all of a sudden you've got a heater that will generate continuous heat 24/7 out of the ambient humidity with no other power input. You need no natural gas, nothing. That's all you need. So have your home, let's say you have got your refrigerator-sized generator for all your other devices. For heat, you've got your power bricks in your floor. For air conditioning, you could do something similar with Peltier coolers, or pick your favorite heat transfer heat pump method in your ceiling or whatever. You can just design this stuff into the architecture, because then you've got this energy. You've got this brick that's an energy source. Then you can use it for heat transfer. If you just want to use conventional methods, just use conventional electric heat in homes. Heck, I've got the space heaters are like old-fashioned radiators that have a thermostat on them, and you roll the thing into the room and just set the ambient temperature. You could just have all those, and then have your mammoth-size, refrigerator-size power bricks in your basement or something if you want to power them all conventionally. Because then you can just hook it up to your breaker box in your basement, unhook it from the electrical line coming in from your utilities, and just hook it into your own local power system. And then you can run all your space heaters off your own power grid. It's just your energy consumption went up. But anyway, I'm rambling. I just wanted to go through some more of these examples before I go absolutely crazy here. Then I got into electric cars and trains and scooters and things like that. I wanted to see how that compared. What size would you need? So with our current technology, basically, there is actually a direct conversion between watts and horsepower. 1 horsepower is 745.7 watts. Okay, so that way you can figure a car needs a 50 to 100 horsepower engine, if you want a snappy car, you need 150 horsepower. And so for a basically fairly slow electric car, it takes a while to get going, but it'll still operate at conventional speeds on conventional roads. You would need about 50,000 watts. Okay, that's very doable, very conservative. That would take about 1,220 cubic feet with their current designs, which, if you do the math, it's like, I don't know, the size of a school bus or something. And theoretically, you could get it down to 50 cubic feet, which would be more like the back of a minivan, what that would hold. So what I'm getting at is you're getting doable. This theoretical number will probably never be able to get there. The way things work in real life, you can only get about half theoretical usually. So even if it had to be double that, then let's say, okay, you'll need a slower vehicle. It won't be as snappy. It'll take it longer to get going. But you could this is continuous power output. So like I said, with capacitors and batteries, you could have some high-powered capacitors for that initial acceleration and stuff. And just figure out that your design and engineering, then you'd get the size of your power backs down to a fifth or a tenth of what you'd normally need. So what I'm getting at, this is very doable, okay? It's going to be bulky and impractical just with their existing first stab prototype technology they've got. You get engineers out there, you start to get this stuff optimized, you're going to get down to a vehicle that can practically hold one of these power cells, okay? You're going to have an electric car that doesn't need batteries. You're going to have an electric car that generates its own power. So, therefore, you've got infinite gas, you've got infinite range. You might have to take breaks every once in a while, let it recharge, depending on how it's set up. But again, you get enough power breaks, you can get it to where it can provide enough power to sustain you on level ground. And then when you've got hills going up and down, you can have more discharge and more recharge and have capacitors to smooth that out and stuff like that. Or batteries, if you really need to. But what I'm getting at is you can do this with the capacitors, so all the downsides of batteries can be gone. That's the biggest downside of electric cars right now is batteries, because the batteries only last so many years, and then you've got to replace them all, which is hugely expensive, which ends up making your electric car more expensive than a gasoline-powered car. So there's a lot of room for improvement there. And what I'm telling you, what I'm getting at is you get this dialed in, we're going to have devices that run on their own power practically indefinitely. Okay, and I'm just going down the list here. Scooters only take 350 watts. They would take about 8.5 cubic feet. I don't know, about the size of a motorcycle chassis to generate the power. Now, you can get that down to 0.35 cubic feet, which would be about the size of a skateboard surface, and then get a deck that's about an inch thick or something. That would power a scooter. Your hoverboard. That's definitely doable. We're getting to things that you don't expect as fast of acceleration, so then you don't have to have as much power output. And then my last example was an Anker battery. The battery used to recharge your cell phones. The great big mammoth one they've got that's about the size of a king-size candy bar or something. That puts out, it was something like 25 watts. So with their existing technology, you'd have to have something about the size of a car battery to give you that kind of power, but it would give it nonstop, okay? And then optimally, if you get this optimized, theoretically, you could get that down to a brick that's about 14 inches by 3 inches by 1 inch. So it's about the same size as the existing Anker battery. Okay, and practically it might have to be double that size. Wham. Okay, so double that size. You got something you can fit in your backpack that will power all of your electronics, your backpack or your purse, whatever, belt pouch, will power all of your electronics to take with you on the go. All your mobile electronics. Laptop, you'll need something more like a, car battery, briefcase, something, whatever. And with existing technology, you can optimize it. This stuff all gets to be practical, because then you can power a laptop with something the size of a textbook or something like that. So the short answer is, with this technology, would devices be able to be as small and thin as they are now? No, they would not. and not if you want the device to generate its own power and be completely independent from recharging and anything else. But they could be close. So I could see a day 100 years from now, or probably a lot less, where we're just used to the idea that portable phones are a little bulkier. Okay, it's a little bulkier, but we're figuring out ways to make things more power efficient. So I could see having more and more efficient phones that are getting smaller and smaller. So I could see maybe 10, 20 years having a phone about the size that the cell phones were in the late 90s, early 2000s, bigger, more like a cordless phone, a wireless phone, that kind of a thing, that would generate its own power, especially if they just have to be a cell phone. Heck, if they just had to be a cell phone, they wouldn't require as much power as a smartphone, and you could get them a lot smaller, maybe more of a candy bar phone size kind of thing, practically, in 10 years or so, that would run under its own power. And then this carries over to everything, vehicles, electric lights. I mean, I can, basically what this gets to is you can manufacture every powered device to include its own built-in power generation. So you no longer need electrical wires to transmit power. Okay? I mean, you can say, oh, we don't need that now because you have wireless power. What I'm saying is you're not transmitting power from point A to B anymore. Every device would generate its own. Okay? Powered loudspeakers would generate their own power. Electric lights generate their own power. Space heaters, refrigerators, microwaves, televisions, computers, you name it. Everything would have its own built-in power generation. So you buy a device and you turn it on, it just works. You never have to plug anything in. You never have to charge anything. Everything becomes portable. Everything becomes off the grid. And everything would theoretically run indefinitely. You make things solid state. That was one thing these guys discovered with this technology is you're not, they did all the experiments to verify that they weren't degrading the nanowires. It's not like molecular components of the nanowires were getting eaten up in some reaction to generate electricity. You weren't getting material from your electrical plates that was getting eaten up, the conductive plates. There was no material consumed except water vapor, and that wasn't even consumed. It was more like recycled. Basically, the water vapor would establish a gradient because of the properties of your nanowire mesh, that if you prohibit water vapor from coming in one side, only let it come in the other side, then you just naturally get a gradient. That gradient will naturally generate electricity. And if you're drawing current from that, so you got electrodes on each side, you're pulling current off of it, the system, when they did the research, this has to do with proton transport through the mesh and getting protons from your networks of water molecules that are kind of hydrogen bonded to each other. And you basically get your protons going down, and then you get your cationic, positively charged water molecule conglomerates on top, and all your protons end up going down to the bottom of your gradient, and then your electrical current goes down. And basically what they discovered is after about 20 hours, your voltage goes down from like half of a volt per cell down to 0.3, about a third of a volt per cell. And at that point, they found out you turn off the power, it'll naturally reestablish the gradient, and your protons migrate up, establish equilibrium, and it'll reach its start point again in 5 hours. So basically, they had 20 hours on, 5 hours off. So you're telling me, oh, aha, this is not practical for a device that needs continuous power output. Before I get onto that, what I wanted to mention for that last point was that basically the point is there's no material being degraded. Okay, there's nothing being eroded. There's nothing that's deteriorating or oxidizing over time or anything. So this is an indefinite power source as long as you periodically let it recharge. So you tell me, aha, yeah, you can't get continuous power out of it. You have to let it recharge for 5 hours out of your 20 hours of use. Or, 4.5 out of 19.5, 24-hour day, whatever. And I tell you, well, wait a second, this really just has to do with your design, okay? You can design your power brick so that it's actually got 25% extra cells in it, and then it's just cycling through the cells. You can design this with some very simple logic built in. They even have some demonstrations for how you can design logic circuits using just the thin film mesh and stuff with some transistors. So you can get very simple with your logic design, and that means it's very robust and it's not going to deteriorate over time. So you can have simple logic built in that cycles your power. Basically, you can have these set up so once your voltage within a cell gets below a threshold, let's say it's like from 0.5 volts, let's say it gets down to 0.4 volts. And you can say once they're down below 0.4 volts, it switches off, okay? And then it'll let itself recharge. And the rest of the cells then will be taking up the slack. And the point is, they'll be eaten up probably fairly randomly once you get this going. And then you could just it'll just naturally be cycling things off when they need to be cycled off. And the point is, you divide this into fifths. 20% of the time, things need to recharge. 80% of the time, they can be active. Well, then it's no problem. You just have like a 20% extra built in to your design. And it's naturally going to be able to, with switching logic, it's naturally going to be able to continuously generate power and periodically regenerate all the cells as they need to be. So you'll have a brick that'll sit there and put out your, let's say it's 1 cubic foot, and it'll put out, however many watts that is, 41 watts per cubic foot with their current design. And you can get it that theoretically has a limit of 1,000 watts per cubic foot. So with practical engineering, you probably get to 500 watts per cubic foot. You'll have your brick, and so it has to be 80% bigger than a cubic foot to generate your 500 watts, whatever. It's going to be outputting 500 watts nonstop. So if you've got some floodlight on a football field, and I don't know, you're in Alaska and it's in the wintertime. Let's not be football, maybe it's curling or something. Something you're doing outside and you need it lit up 24/7. You got some beacon. Let's say just for the hell of it, you got the Christmas display, Christmas lights on your home that you just want on 24/7, and they're going to require 500 watts of power output. Well, there you go. You got your brick set up. It automatically refreshes itself. The nano cells automatically refresh themselves periodically as they need to. So basically, you have this brick that sits there and generates 500 watts nonstop till the end of time. As long as your ambient humidity stays around 50%. Now, I thought of some interesting ideas with that one, because what it looks like is the water vapor is not consumed, okay? You just need a certain amount of ambient water vapor as a sink for it to draw on until these things need to be recharged. And so basically, you need a certain amount of ambient water vapor in a certain volume. So in your power brick, your generator, you could have the whole system be sealed, and it would have this air chamber inside with an ambient humidity of 50%, which is their optimal, right? And you could even have a little source of water in the bottom if you need a little reservoir or something for it to draw upon, whatever you need. Because the point is, as it cycles through, generating power and then recharging, generating power, recharging, there's no net consumption of water. So the point is, you can have a closed system that has the correct environmental humidity built into your power brick. At that point, you don't need ambient humidity to be anything. It can be completely dry, completely wet. But even if you don't want to have this more expensive power brick with that built in that has to be sealed, you can have one that relies on ambient humidity, and your average humidity, even in the Sahara Desert, gets down to like 20%. which this stuff will still function, like 30% optimally of its output or something. And even if you're in, a lot of times it's 100% humidity, like in summer when it's really humid out and stuff, you got rainstorm going on, monsoon season, there are environments around the equator, there's always almost 100% humidity. This stuff operates like, again, 20 or 30% efficiency, something like that, at 100% humidity. So you're fine. Well, my point is that any ambient humidity on the planet outside, this stuff will operate nonstop. So that concern is covered. And what got me so excited here is you just can't find a downside. And this isn't some free energy theory. This isn't some device by Tesla that got confiscated by the government and they're never going to tell us about it. This is research that these guys have been doing for 30 years. That's the incredible part. You can go back and start looking at their papers researching these bacteria and the networks of nanowires from the bacteria going back like 30 years. Okay, and they've been step by step establishing how these things work, how they behave electrically, and then over the past few years, they've worked on this specific technology, using it for power generation, how it works. They've got all the details in here, the chemistry, what's going on. They did their experiments. I could talk about that a little bit. So they tried to address every concern people could have. First, people are like, can you verify that it's just the water vapor that's doing it? So they tried this every conceivable way. They did different materials to try to verify that it wasn't the type of materials in their electrodes. They did different types of meshes to see that gradients were in, and they found out that you have to have a nanowire mesh that has certain types of functional groups, okay, that transport protons and things. And they proved that if your mesh has those kinds of functional groups, regardless of its source, as long as your wires have the correct dimensions and they've got those types of functional groups with a certain density, it will maintain this humidity gradient and it will conduct electricity. They demonstrated all this experimentally. And then they started taking elements of this away. So if you take away the functional groups, but you have the same types of nanowires, which they did, and put that into film, your humidity gradient happens the way it's supposed to, but then all of a sudden you don't get the proton transport and there's no electricity flowing. So they narrowed it down very quickly. They get to the point where, okay, can we verify that it's humidity? So you take your device that's working, right? Slap a piece of parafilm on top of it to keep the ambient humidity out, and all of a sudden your voltage drops down to 0. Take the parafilm off, your voltage goes back up. Okay? Put it in a larger test chamber, take away humidity, what's your output? And they actually did experiments. They've got experiments documented in here with the results and the error bars and everything, where they have different ambient humidities and then a graph showing the voltage and current output as a result of that. And that's how they could find their sweet spot of 45% in a range of 40 to 50%. Anywhere in that range, you get their optimal 0.5 volts output per cell. And then they got their graph elsewhere. I could waste the time to dig that up if I want, but I'll either include these figures. These might be copyrighted, so I'll probably just include links to the paper so you can check it out yourself. You have to pay like $8 just to view the paper on Nature online, or you can buy it for $35. But the 30 pages of supplementary figures, that's all free. You can download that PDF for free off the Nature website, which is cool. And if you're part of an academic institution, of course, then you're going to have a way to get to, you'll have a free subscription to Nature anyway. You'll be able to get in and print out the article. If you're into scientific research, you'll know about all that stuff already. But anyway, so that way you can look at it yourself. And my point is, they basically, every conceivable argument for how this could work some other way was eliminated. And then they verified every single step for how it has to be the way they say it works. It has to be this humidity gradient, this moisture gradient in the nanofilm, and they've demonstrated it all goes hands in hand. The nature of your humidity gradient parallels the nature of your electrical conductivity and everything. This is so theoretically researched. It is just unbelievably bulletproof. It's staggering. But this is what you find. This is why Nature is like the premier research magazine out there, because that's what they demand. You've got to have robust findings that are proven forwards, backwards, right side up, upside down, inside out, outside in. You've got to have every single angle of this thoroughly proven before they're going to let you publish. That's why it took these guys a year to get it published. But they did the legwork, they proved it, and it's established. And if you're going to run off and try to patent this, don't bother. I was reading online. These guys are idiots. They do this kind of stuff all the time. Come up with new technologies and patent it. But I was reading a news article from Sweden or something, and they verified that yes, the researchers actually have already patented this, and they're already pursuing avenues for how to manufacture these devices and turn this into an industry. And people, this is it. This is going to take the world by storm. This is going to turn everything on its ear. And if you have stock invested in energy right now, if you have stock invested in wind generators, any kind of oil production, petroleum, fuel industry, natural gas, anything, now would be the time to pull your money out, because you know what? All those are going to be gone. In 10 years, that's my estimate. It could be a little longer, it could be shorter. We're not going to have electric companies. We're not going to have power plants. We're not going to have fuel. I mean, on any kind of a major scale. I'm sure there'll be some niche market for petroleum stuff for people that want it for something. Probably backwards compatibility for quite a while. But there's, in the future, not so distant future, there won't be oil companies, there won't be natural gas, there won't be natural gas pipelines, there won't be trucks hauling oil all over the place, there won't be trains hauling coal. The embodied energy in materials will no longer affect their sustainability. I took a class on sustainability and green architecture, and the instructor was dead set against concrete because concrete has such a high embodied energy that even though you have this almost limitless supply of minerals out there, of sand or whatever to make your concrete blocks, even if you regard that as sustainable, which isn't really a sustainable source, but even if you regard that as the embodied energy in making concrete and transporting it and things was so huge that it was nowhere near sustainable. Okay, anything that is not sustainable currently, because of the embodied energy, that's no longer going to be a problem. Because once you've got essentially free energy, it's not magic, it's not free energy, it really does come from humidity gradients, but these guys have discovered a material that maintains a humidity gradient without destroying the material. You can extract electricity from it, and it's reproducible, it's sustainable. So embodied energy is no longer a problem. So the materials we use are going to change. The expense of them is going to change. The expenses of everything is going to change. Transportation costs are going to just drop through the floor. It's going to change everything, people. I mean, this is so groundbreaking. I mean, those are just the consequences I can foresee after having thought about this for a couple of days that I've been aware of it. I'm sure there's lots more. It's just going to turn life as we know it on its ear. I mean, why do we need to fight over strategic oil resources around the world? Why do we need to keep on Turkey's good side in the Middle East, in these other countries, just so we can have our fingers in the pie and we don't let Russia get control of all the major oil producers in the world, and if a war breaks out, then they have control of the energy. And as we found out in World War II, if you can starve a country of its energy inputs, well, you basically brought their military to a halt and you've defeated them. Which is why, strategically, we're so interested in the Middle East. That won't be a problem anymore. If everybody can generate the power they need locally, the same all over the planet, there's no limited resource that you have to compete for. Well, people, this is going to change politics. It's going to change economics. It's going to change everything. So I'm beyond excited about this. That's why I had to make this video. No, this doesn't have to do with my normal topic. Actually, it does though, and that's gets back to my interest. So you're asking, what does this have to do with modern channeling? What does this have to do with the raw material? Well, I'll tell you what it has to do with it. In the raw material, which is for those of you who are not New Age types and don't know what I'm talking about, the raw material, in other words, the law of one, as channeled by in the 80s by what's her name? I can't remember the lady anymore. But there was this group that channeled, and this one lady that went into deep trance and channeled the raw material, a psychic source, and they are entities from outside of our planet, from elsewhere, that know about things. And they made some very interesting statements. They don't talk about our planet and just the normal day-to-day things that go on our planet very much at all. They view that as unimportant. They're more interested in the spiritual side of things, and most of their advice is spiritual type advice. But in their discussions, it did come up that they claim that our major countries, namely United States and Russia, have technologies that are like UFOs, and we have craft that are like UFOs, and we have this technology basically because Tesla discovered some radical new techniques before the end of his life, and the government confiscated them. And if you read the history of Tesla, that's exactly how it went down, okay? He was basically shunned by everybody for the last few years of his life, did just phenomenal research for the last 10 years of it. At the very end, when he died, the government came in and confiscated all of his research. And then the day after, they sent in a token engineer from the Air Force or whatever that analyzed the stuff and made a public statement and said, oh, it's all bunk, there's nothing to it. But that research that there was nothing to, well, the government kept it to themselves and didn't let anybody see it. And according to the psychic sources, the raw material, what the government did from then was started building machines and devices based on this technology. And in a nutshell, the point that the raw material made is any energy needs, any needs that you have as a world, as a civilization, can be met at no cost at this time with the technology you have at your disposal. It's that your governments, for strategic reasons, are holding them to themselves. So I was always bent on trying to discover what Tesla was onto and what are the ways of extracting energy from the environment. And I don't believe Tesla was onto, there's no indication he was onto this type of technology. Okay, nothing to do with moisture gradients and nanowires. Apparently there are other more elegant methods that have to do with energy grids that come into the planet Earth that, I don't know, cosmic rays or magnetic fields, whatever, things that are beyond what we can detect or we're aware of at extremely radical voltages and stuff, that if you do it right, you can have devices that resonate with this energy flow and basically tap into that power. Apparently that's what Tesla was into, and that's why I was interested. Well, what I think is so cool about this, because with the Tesla type technology, obviously if you start researching it, you publish that research, the government is going to just, they won't fund that kind of research. They're going to squash your funding. They're going to take you out. They're going to pull the videos off the internet. Because they have obviously done everything they can for the last 50 years or more to keep this stuff under wraps. So they, I'm sure that they would not hesitate to kill people or do anything to keep that under wraps. What the beauty about this stuff is this is a completely different technology, okay? We found, good job, humanity, we found a completely different way to extract energy sustainably from the environment, okay? Practically, efficiently, it can scale up as high as you need it to. We've done it. It's published. the research is already out there. The cat's already out of the bag. This is going to happen, people, and I'm thrilled. I'm just thrilled to death that finally we're going to have our effectively free energy. We're going to get rid of the power companies. We're going to get rid of the grid, get rid of the system of control, okay, and give people the independence they deserve. If you want to just grab a plot of land out in the middle of nowhere and plop your hut and be completely off the grid, now you can do it and have your energy too. You can have your heat, you can have your electricity. I mean, what does this mean? This means you can have electricity to power your growing lights to grow things underground for hydroponics, indoor greenhouses, which means, yes, if you want to hunker down and build your bomb shelter and isolate yourself from the universe and have air recirculation devices which require power, like on a space station or a submarine, yes, you can have all of those, all of them running from this sustainable energy source that's completely off the grid, and you can just knock yourself out, okay? Hole yourself up, live wherever, however you want to do it. You want to make the devices, this is how. The tricky part is the nanowires. Oh yeah, and finally, you might object, oh, but this is going to be insanely expensive. Now, yes, people could charge, and these guys have the patents, they could charge an insane amount for it if they want. There's nothing to say that they will. But as far as the actual cost of manufacturing the technology, yes, these geobacter bacteria that they did the experiment with to grow the nanowires, because that's what natively grows the nanowires. Yeah, it's kind of tricky and finicky and requires specific environmental conditions to grow them and be kind of expensive. But one thing they proved that they point out in this paper is that they genetically modified a strain of E. coli, which is the common bacteria that just grows everywhere. Okay, they got a strain of E. coli running that that makes the nanowires the same way. So now you can manufacture these nanowires with E. coli off of chicken noodle soup or whatever. I mean, it's nothing. Okay, and they'll sit there. You can have your there's mass production with this kind of technology already, where you have biological organisms in one part of your assembly line making a soup, and you siphon off part of the soup continuously, and to manufacture what you need to manufacture, and then you have an input into the soup of more nutrients, and the bacteria just grow on a regular basis, so that's sustainable. So you basically have this cell that's generating the material with just your food, whatever your source is as input. So basically, for the cost of sugar or something to feed your bacteria, whatever's cheapest, that's all it's going to take to grow these nanowires, and it doesn't take that much. Okay, it's so just off the top of my head, my rough estimate is that it would cost them $20 to make a 1,000-watt generator the size of a refrigerator. 200 tops, okay? And so let's figure a 100% markup for less than $500, for less than the price of an air conditioner, about the same price as a good air conditioner or a refrigerator. You're going to be able to have a device that will generate all the energy needs for your home. I mean, and then we're talking about devices having this built-in. That's that's it, people. The future is here, and the future is called protein nanowires. Look out, world. Here they come.